while. It's been quite a while, so it's fun to be out here again. So today I'm going to talk about some work that's going to appear soon with my student who's now graduated, David Kolchmeyer, and Government Chanoff and Julian Sonner. And so the idea is to, from one point of view, add matter to the story of science checker in Stanford, which of course is well known here. So to add propagating matter to the gravity side there and find an associated matrix model in this more general situation, and it will be a multi-matrix model. From another point of view, what I'm going to do is take the ETH, the Eigenstate Thermalization Hypothesis, which is some statistical ansatz with the matrix elements of simple or light operators between high energy microstates, and reinterpret it as a matrix model, which will, on the one hand, tell us that that the usual Gaussian ETH isn't even sufficient for being field theory, so it's kind of has to be corrected into something very non-Gaussian. The non-Gaussian thing will still be integrable, so it'll be some kind of integrable to matrix models about which we can say a lot. We won't completely solve this matrix models, but we'll say a lot about them. And just like in the SSS story, the TOF diagrams of the matrix model have a nice geometric interpretation. And the two matrix model that I'll talk about will kind of develop from taking as input correlation functions of the gravity theory in the disk, but then we'll use the same model to do computations at higher genus and get some interesting answers. So that's kind of the general trajectory. So first I'll kind of start from this ETH slide once I get into it. And then in a sense, we can think of JT with matter as an example. I say it like that because I think the same kind of structure will apply to higher CFTs, just with some extra ingredients, but there'll be, I think, a similar story for higher CFTs. And at the end, I'll even have some speculative comments on further aspects in that direction. So later. And then, so we'll start at the disk. The disk is more complicated for multi-matrix models than for one-matrix models. So there's kind of quite a bit to say already at the disk level, but then I'll discuss higher genus and then conclude. So, okay, this is like a super introductory slide in case there's someone in the audience who might have been, since it's called the SITP colloquium, I wasn't sure exactly what to be here, but this is probably not necessary. But anyway, the properties of high energy microstates of chaotic quantum systems are pseudo-random, in the sense that if you look at the spectrum in the thermal range, it has a very large density, very small level spacing, e to the minus s, whereas it's some microscopic entropy, and the energy levels look like pseudo-random numbers, not drawn from the Poisson distribution, but from something exhibiting level repulsion. So it basically looks like the eigenvalues of a random matrix. And then if we have other observables, not just the energy, some other light operators, their matrix elements between the heavy states will also look like pseudo-random matrices. And here I want to talk about the statistical properties of those things, and it's natural to code them as a matrix model because a matrix model is a statistical ensemble of random matrices. Somehow the ETH was not usually phrased in the language of matrix models, basically because people write the matrix elements in energy eigenbasis. And so when you take a multi-matrix model and you write it in the eigenbasis of a single matrix, it makes it look less SUN invariant, and it's the size of the matrix. And so the matrix model aspect is perhaps slightly obscure in the ETH literature. So we'll kind of first rephrase the ETH in this language, and then we'll go from there. And the nice aspect is that, at least in the holographic theories, this matrix model extension is related somehow to the bulk geometry. So we could say that the work of Douglas and Steve and Phil is that the old matrix models, related to the gravity, have a Wigner-like interpretation, right? Because in the old matrix models, it wasn't clear what the matrix was, and what you and they saw was that it's the dual Hamiltonian in the sense of the CFT. And so kind of the way I'll think about what I'm going to do here today is that we're going to unify the ETH in the same framework, basically, and it will also have a geometric interpretation. So the idea is, imagine we know some low point thermal correlators of light operators, or the correlation functions in the black hole background, in the radius short background. And I'm going to sort of start speaking rather generally, and then later we'll focus on the JT example. So this could be higher dimensions. So what are the thermal correlators? Well, it's trace and Boltzmann ensemble is a product of a bunch of light operators, which I'm calling curly O, at various times, tau 1 to tau n. They could be Lorentzian times, Euclidean times. That's kind of the data of the thermal correlators. And we can think of it as, if we computed it from the microscopic theory, then we would have to know the matrix elements of the operator. Oh, is there a pointer actually? So I don't want to. If not, it's okay. If it doesn't bother you, then I'm happy to.
Right. There used to be a stick somewhere. Maybe it's gone.
I don't see it, but that's okay. Hopefully it's not. I'm trying to avoid standing like right here. Okay. So if you knew the matrix elements of the light operators between the heavy microstates, then you could just plug it in to that formula, sum over all ETH microstates, and compute the correlators. But of course, we're really in the opposite situation. We usually know these correlators, which is a relatively sparse amount of data, and we don't know the E to the S by E to the S matrices. Okay, so one way we can understand why there's sort of an ensemble is that we could ask, given those correlators, what is the maximum entropy ensemble which is compatible with those correlators? Because this is much less data than the E to the S times E to the S data, so there are many matrix elements consistent with that. At least if we say that we only computed up to. We only nailed them down up to E to the minus S corrections, something like that. Alternatively, you can think of generating an ensemble, and this is the way it's usually phrased in the ETH literature, I believe, by picking exactly which small band of energy levels you consider. So I kind of average over exactly which energies I'm looking at, and that defines a kind of ensemble. But I think in a way, the statement that you have a theory which is chaotic in this sense is the statement that the ensemble defined like this, the maximum entropy ensemble consistent with the light data, is the one that the theory has if you ensemblize over exactly which narrow band you consider. Those two should be the same ensemble, is really the statement of that it's a chaotic theory. Okay, but I'll assume these two things are the same. And so the kind of the conjecture here, for which I'll flesh out in the case of JT gravity, where it was matter, is that there's a single trace matrix model for, okay, so we should distinguish between what happens for holographic theories and what happens for general CFTs. So for holographic theories, there will be a single trace matrix model for all of the primitive light operators. Primitive is what people usually call single trace. But I don't want to use that word because I want to use trace to refer to trace in the speak over space, not some large theorem. So in the holographic case, it looked like a single trace matrix model for all of the primitive light operators, including the stress energy tensor, which is the Hamiltonian. And instead of being Gaussian at infinite C, where the answers look like thermal mean field theory. Thermal mean field theory, by thermal mean field theory, I mean that the thermal correlator is factorized to the 1 and 2 point functions, and then you sum over all wick contractions. The matrix model, which gives you thermal mean field theory, is very non-Gaussian, including for the operator O, but it will be integrable, although not Gaussian, in a very specific sense that I'll explain. And so, and then if we take 1 over C perturbation theory, we get corrections, 1 over C corrections away from this integrable matrix model. And then if we have a generic CFT, which I won't talk about today, in a generic CFT, we would expect that you have to have a matrix for every Lie operator, not only the primitive ones, because there isn't any specific notion of primitive operator in a generic CFT. Right? There's no distinction between multi-twists and we're all on the same footing. And then you'll have many more matrices, but a very similar structure. But maybe I'll come back to that a little bit at the end if it's fine. Okay, any questions about sort of this? So how does the ETH work? So it's a matrix ansatz for the matrix, sorry, it's a matrix elements of the line operators and energy eigenbases that's designed to reproduce the thermal 1-point functions and the thermal 2-point function. So the 1-point function is easy. If I have a thermal 1-point function, it basically means that I have a part of my operator which looks roughly like the identity matrix in a given microcanonical band. In other words, just has some non-zero value. So that's what this term is. This is like a classical value for the operator O in energies of range EI. And this thing can depend on the energy, but it's supposed to depend on the energy slope. Like not from microstate to microstate, but it only depends on which microcanonical band I'm in. So that reproduces the 1-point functions. But of course, if I have that as the whole thing and I computed the connected 2-point function, I will get 0. So we need something else to give the thermal transport, the 2-point function. And so the ETH ansatz looks like this. So we have some kinematic factor of e to the minus the entropy over 2, and then a smoothly varying function of the energy and the energy difference. And then a random matrix Rij with norm squared 1. Now, you might say, in a sense, it's just a definition of this function or something. But again, the point is that the function f is slowly varying. It doesn't know the details of which microstate you're in. And in a specific system, of course, Rij is not really random matrix, but pseudo-random matrix. But if we take the point of view of the earlier slide, that someone just tells us the light data, and then we find the maximum entropy ensemble consistent with it, then Rij would be truly random. And so from this, you can compute the connected to correlator. It's easiest to do in the microcanonical ensemble, but you can just Laplace transform it to get the visual canonical ensemble. And there's an overall e to the minus s, which is just the 1 over trace of 1 in the microcanonical window. So that's the normalization of the correlator. And then we have a double sum over states. You have this random matrix Rij, Rji. You get this factor of e to the minus s from this thing squared. And then we insert one of the operators at a time t, so we get some energy factor, and then this function squared. And then there are other corrections that are further suppressed. So this formula looks weird. This should have said plus other e to the minus s over 2. In other words, further corrections that might not be captured by the ansatz. And this first term, and I'm ignoring here the 1-point function because that's not trivial, so it's 7 to 0. And then this first term clicks with the Gaussian mean. So in other words, if we average over the ensemble, then Rij, Rji turns into 1. And then this double sum over Rij gives the factors of e to the s to cancel those. That's why the minus s was put there. And you get a simple formula like that. So we learned that f squared is just the Fourier transform of the thermal microcanonical 2-point function. Okay. Now, in this story, one can think of what's happening at different timescales. If you look at very tiny energy splittings, then you're just talking about random matrix statistics, which is related to ultra long timescales. That's not going to be sensitive to the function f or any other corrections that appear in this formula. That's extremely universal. The function f is really non-trivial only when the energy separation is of order the temperature, because otherwise the 2-point functions go to 0 at time is much larger than the thermalization time. And, maybe unless I'm in a system with conserved currents, and then there could be some pieces of this function f associated with conserved currents that are longer lasting and so on. But there are any details in here. I'm just sketching this, and then I'm going to focus on the case. But here I just want to get the physics at all times. When I say all times, I mean, okay, I will not expect to reproduce from the perturbative expansion of this matrix model things at timescales that are order exponential in the exponential of the entropy, which know about the actual underlying microstates, first and averaging of that. And if we had a system where the UV looked free, so like if our system here was a free theory with some specific operators in the UV that then flows to, say, a CFT, we would not expect this to work in the UV. So in other words, at extremely early times, where you, very short times, when you will see the, like, some underlying UV Lagrangian, we'll also not expect this to work. But if we have a system that's like a strongly interacting CFT, so there's no weakly coupled UV, then this could work at arbitrarily short times. So that's kind of the domain which this discussion is. Well, perhaps to get short time in a theory which looked weakly coupled in the UV, it would be like a matrix model with so many constraints that it starts to fix the matrices. Right? Then you know that they obey the underlying Heisenberg equation with some sort of evolution. And of course, in the story, if we want to think about something like scrambling, we have to look at the 4-point function, so it's already beyond this usual ETH discussion. Okay, so that's the ETH. But it seems very natural to reinterpret this thing as a matrix model. We can say that we have a combined model for the Hamiltonian and this operator model, and there's a matrix potential for just H, which, in the case we're talking about soon, is going to be SSS double scale potential. But more generally, it's some matrix potential which is determined to match the smooth spectral density of whatever the system is. And then there's the part of the potential that involves H and O. And the conventional ETH is just quadratic, right? Because it said that it was a quadratic random matrix, and that was the whole story. So we'll look at Gaussian and O, but it will be a complicated function of D. Now, this potential is a single trace potential. We're just writing it in energy eigenbasis. And the point is, I mean, if it's not obvious, I mean, the point is that any function of two variables, so it's kind of like, if I wrote it in a single trace way, it would like trace OH, OH, or OH to the n, OH to the m, with some coefficients a and n summed over a and n, any function of the two energies can be expanded like that. And you don't have to use power laws. I mean, just anything, right? So it's a single trace potential. And if we were talking about higher DCFTs, which I would not, everything would be graded by spin. So the idea of higher D would be I will use the state operator correspondence to label my heavy operators with correspond to states and radial polarization cylinder. They will be labeled by spin and dimension. So I will, for each spin, I will have the dilation operator in that spin sector as a random matrix. That will be my H graded by spin. And then the operator O will have matrix elements between every microstate and every other microstate, each labeled by spin and other energy label. And so we just get some big graded matrices. And as I said before, the expectation is that in holographic theories, the multi-twist operators will be constructed just as products of the matrices for the primitive operators, so you won't need to write the matrices for them. Or alternatively, if I had the bigger structure where I have a random matrix for every operator, integrate out the ones associated to multi-twist operators to generate a simpler guy. And in general, when I integrate out matrices, I get multi-trace terms. But in the special models that were holographic, I would expect I don't. Yeah.
You expect analysis spin to be important.
It's probably important in the construction. Well, that was I'm sure it's important in the conjecture that I just made that in integrating out the multi-twist operators in a large C theory, you end up with still a single trace model for the current operator. Then the fact that they are close to GFF trajectories would be pushed. In a general CFT, I'm not exactly sure what role they would play, but we haven't studied general CFT. Okay, so how does this what's sort of the first wrinkle? The first wrinkle is that the Gaussian ETH does not give thermal mean field. So you might somehow probably, I don't know if anyone claimed this, or it was just my overinterpretation of what was being said in papers about ETH. But before I started thinking about this, I certainly thought that the Gaussian ETH would be associated to thermal mean field theory, where the thermal correlators are the sum of Wick contractions. But that's not the case. How can we see it's not the case? Well, so first let me just tell you what the Gaussian ETH does give you. It gives you the sum over only two Wick contractions, but not the cross one. So let's understand it in two ways. First of all, in the usual language of the ETH, how do we get the product of two two-point functions for the four-point function? Well, the four-point function is something like this, right? And the functions of time and energy are included in the kinematic functions. That's what the e to the I, t, delta e's, etc. But we're just going to focus on this discussion of indices. So in order to click with the Gaussian ensemble in the Wick contraction that brings the first two together, we have to have k equal to I, right? And that will also make the second two automatically click. So you pay one factor of e to the s. So similarly, if I have the contraction of the middle two together, I need to take j equal to L, and that also makes both pairs click, and that pays one factor of e to the s. But to get the what we might call the U channel, where this one clicks with that one, you need to have I equal to L, and j equal to k, and j equal to I, and that just sets all the indices equal, and I paid three factors of e to the s. So that diagram is down by e to the minus 2s, and it's zero at the planar level, right? So it's basically like the out of time ordered correlator just vanishes at t equals 0, sort of instantly scrambled. Now, that in a way might not be too surprising because we just picked the matrices at random. And so if we pick a matrix at random and then we evolve it in time by a little bit, the chance that it's going to sort of play nice with the original matrix when it didn't evolve in time seems very slim. Because why would it? We just pick them at random. So it kind of corresponds to a theory with scrambling time equals 0 and a thermalization time which is longer, so it's not very physically sensible. From the point of view of matrix models, it's extremely clear because if you look at the 't Hooft diagram extension, if we want to try to write a planar 't Hooft diagram for this four-point function, because the model was quadratic in O, the O lines can't cross, so there's no contribution. The e to the minus 2s thing is something where you put a handle so that one line can get around the other line. Configurations like this we studied by Sound in some paper, as well as others. But although those contributions might be important and interesting at very late times, it means that this ETH has failed at early times, like it altered the thermalization time when the function f was relevant and important in the game and so on. So if we really want to reproduce all the correlators, this is a problem that we need to fix. Right? And all it's telling you is that the model is not Gaussian. So it has to be some non-Gaussian two-matrix model. And that's perfectly fine, except, of course, in general, two-matrix models are not solvable. So if it's Gaussian, one of the matrices is easy. You can integrate that matrix out. You still get an eigenvalue of the other matrix. With generic and Gaussian two-matrix models, nobody knows how to solve them. So in other words, if somebody gives me the matrix potential, I won't be able to compute the correlators of resumming the planar total. This model will turn out to have some integrability that makes it better. But it's that I have to say it took us a very long time to understand. That was the biggest instruction. And we can also understand why the thing had to be not Gaussian from a different point of view. From a different point of view, which is in mean field theory, there are an infinite number of operators. We say that if I look at the commutator at 2 times, if I look at the causal propagator, it's just proportional to the identity operator as an operator. So, if we were talking about CFTs and we had in mind the generalized free field theory, this is because in the OOOBE, the only operators that would sit there in a GFF are the identity operator and the O double traces. But the O double traces have dimension that differs from the 2 poles by an integer, the number of derivatives that we added. And so therefore, when you analytically continue to learn signature, they don't contribute to the commutator. Right? There's no non-analyticity in the functions of space-time, Euclidean space-time, so they don't contribute to the commutator. But this fact is kind of obvious if we think of the theory as a free theory, because it just says that when we make a perturbation and we measure its effect later, it just perturbs the single particle to single particle. It doesn't get any other operators in there. Now, but this is true for all time. So it's really an infinite number of constraints on the matrices H and O. And if we pick O at random, it wouldn't obey this constraint. So you need a matrix model with quadratic constraints, which is therefore not a quadratic model. And the simplest thing you could imagine is to take the square of that constraint and add it to the matrix potential with a large coefficient that you try to dial to infinity. In the limit, you will be imposing the constraint. But that will make the model quartic. And quartic is the minimum that you need because it allows 2 O lines to cross, and then you can generate unit diagrams. But the thing that's complicated is that once you add this quartic vertex, now I have to draw all the tough diagrams with quartic vertices. It's like 5 to 4 theory, and you have to sum all of them, and how do you know what you get? Right? But that's the verdict on the ETH. So to be clear, the story about the ETH in this language is that if you have something that looks like mean field theory plus corrections, then you'll start with this kind of quartic matrix model with these constraints, and then you'll perturb it by the other corrections. There's the intrinsic 3-point correlates.
But if you just add this square to V, you won't get the factor O top, right? What O top did you get?
You might, but I mean I didn't get there yet. The problem is the point is that adding this thing to V, of course, with huge coefficient dial to infinity will enforce this constraint, but it will. I mean, it might mess other things up because you have to sum all the diagrams. So there's the question there, which I'm going to come back to in a minute. Maybe you mean here I'm just talking about the field theory. So here the OTOC is 1. In other words, the problem here was not that I had a matrix model that looked like a system without scrambling, and I needed to add something to say scrambling. The problem was that the matrix model gave instantaneous scrambling, and I needed to do something different to get the theory with no scrambling. So adding this constraint will make the theory look like there's no scrambling. So the OTOC will be just the U-channel diagram with no scrambling. Scrambling will come later. So. Well, that's okay, because here I'm just talking about the field theory. So I didn't discuss coupling to gravity or any interactions.
How should I think about this G? One form of within that matrix model with that constraint and then assumption.
Right, well, it depends on what you take as the input and what is the output. So here I kind of imagine that somebody else had a system that they computed or measured that looked like thermal free field theory with a particular causal propagator. That's the J. And I'm trying to adjust the matrix model to match it. That's kind of the spirit of the ETH. But if we knew the matrix potential, then indeed you have to compute the G, and that might be complicated because you have to go between the chordate potential and the 4-point vertex. And so on. That might be a hard problem, but I'm going to discuss how it simplifies. But a priori, it sounds like a hard problem. But since we're not really interested in util theory, I think now I want to switch to a more interesting physical case where we try to apply this to JT gravity with propagating. So here's the JT gravity action, which I'm sure everyone here knows very well. Oh yeah.
General question. So you mentioned integrability. Does this notion that you're finding have anything to do or not with the integrability at the later level of state?
Well, I didn't explain the integrability yet. So I think what I do will be clear. But basically, this matrix model has vertices that obey Yang-Max's equation and Lyson. So it's integrable in that sense. But of course, this matrix model is not directly related to the matrices. These matrices are ETS by ETS matrices. So, but it's integrability in a very conventional sense. That'll explain itself.
When you say the integral theory, you know, what that takes on the gravity side, what does that mean?
Well, it means just free fields and some background.
Okay.
On the gravity side, it would mean exactly free fields on some background with no coupling to gravity. But the coupling to gravity is going to come out.
Okay.
And there'll still be a constraint, just modified a little bit. So that was a sort of a one. Okay, so now we're going to take JT gravity with some scalar, massive scalar that's minimally coupled. It doesn't talk to the dilaton, it just talks to the metric. And if we thought of it from the point of view of AES CFT, it looks like the matter field gives you conformal quantum mechanics, where the dimension of the operator is usual AES formula, AES2, and then that would be the GFF quantum mechanics. And then, but it's coupled to the Schwartz. So that's the JT gravity part. And then you could try to do computations in this theory. So for example, if we stick with disk correlators, we should also compute the scalar one-loop determinant for the disk. That turns out to be not very interesting because you get an answer proportional to the area of the disk. So it just normalizes the effective G movement of the JT gravity. So the relative coefficients of the phi b and percentage. So it doesn't get anything interesting. And so therefore the matrix potential for the Hamiltonian is the same as for pure JT gravity. That's kind of a coincidence of this example. In general, we add matter, will have a non-trivial loop determinant in the Euclidean black hole that will change the spectral density, just happens not to happen. But now, of course, at higher genus, the determinant just blows up when cycles pinch. It looks like when the cycle pinches in the bulk, it's like a very high temperature limit of the matter theory. And since if the matter theory in the bulk has some, non-zero central charge, I get a divergence that looks exponential. It looks like exponential of 1 over the size of the shrinking cycle, and that's a very bad kind of divergence. That divergence corresponds in the matrix model language to what happens when you do the integral over H. Okay, so I'll come back to it later. For now, I want to focus on just doing the integrals over the matrix O with fixed H. Those will not generate any divergences. Another way I could think about it is, for at least some computations, if I went to the B basis, B meaning the length of geodesic cups, then I won't have any divergence. And if I look at the pair of pants with fixed B's, there's no integral. I get something finite. I can reproduce that finite thing. So this matrix model will have exactly the same divergences as JT coupled to matter, And both sides will have to be regulated. And I will talk about some regulated matrix models, some of them with slightly different physics, and we'll kind of leave that for now. So we'll imagine we're just going to focus on doing the OM. So again, the philosophy is to take the gravity answer as a kind of input to fix what matrix model we should discuss. It's the thing that tells us what we want to understand, what is the statistical ensemble from which we should draw the high energy data to be consistent with the gravity input. And so we need to know the disk amplitudes, and the disk endpoint amplitudes of JT with a scalar are given by a sum over, Feynman diagrams, but in the Feynman diagrams here just look like width contractions, except that every time two scalar lines cross, you get a factor of the 6J symbol, which is the out of time ordered term. Okay, so it basically looks like you're just dressing up free width contractions of the scalar with some functions of the energy which encode the exchange of the boundary gravitons. Okay, so this was understood in Jafferis, a really beautiful result. But this is an input into the story today. But again, it's similar to in 3D gravity, where you can where in the dual CFT language, you have something that would be like a GFF, except that it resums all of the stress energy products with stress energy. Here, that sums all the products with the Hamiltonian, which is the only component of the stress energy on mechanics. And so that incorporates the JT gravity of the short side. And the propagator looks like this. So if you have a diagram with no crossings, then in energy eigenbasis, so in other words, if we don't compute it as a function of times, but as a function for energy, as we did with Fourier and the Laplace transform, then it looks completely factorized, even including the effect of JT gravity. JT gravity only couples them because you have to integrate the energies over, integrate the energies with the spectral density. And in this notation, S is the square root of the energy. Here's everybody in this formulas. And when I write this with the plus and minus, I mean the product of 4 terms, each one with plus and one with minus, in every combination. This function is perhaps familiar to anyone who studied end of the world rays in JT gravity. If I deleted this factor, that's kind of the effective potential we get from end of the world rays. It's not really a coincidence because in 2D, if I have a propagating particle, it's like 2 members of 1. I think Jambin made this point in some of his papers. So so what does this mean as far as this constraint? Well, now the constraint is more complicated because it's not just in field theory anymore. There's like a non-trivial crossing term. So what we can write the constraint in the following way. We have our product of 2 O's, and then these are supposed to be projectors onto a narrow band of energies put between them. And if we exchange 2 of them, we're supposed to act with this 6J symbol. And then the resulting thing is just a function of energy. Whereas in mean field theory, the 6J symbol would have just been some delta functions that cross them without any non-trivial function of energy. So this is the difference. That you have this thing here is the fact that now there's a non-trivial crossing kernel instead of just the trivial crossing of the GFI. But because there's a constraint, it's again clear that Gaussian can't be sufficient, and that one needs some Cordic term. And again, the simplest guess would be that you just take the square of this constraint, write it as the left-hand side minus the right-hand side equals 0, take the square and add it to the matrix potential with a big coefficient, summed over all the energies. That thing will generate terms of a particular type, that will generate a quartic term whose, when we have a quartic term, it consists of 4 O's and then a function of 4 energies. That's what a single trace quartic term looks like. And from the constraint squared, the function of 4 energies will consist of some pairwise delta functions and the 6J symbol as a function of the 4 energies. Now, it's tricky to be right. So, but now that's the potential of the matrix model. We have to solve all the matrix model diagrams. So you might wonder, what do you get when I take some 52 loop diagram, some giant nest of junk made out of that 4-point vertex? What does that mean? And so the thing that saves the day is the fact that the gravity Feynman rules are very nice. So that if, first of all, if you have a crossing like this, it equals this diagram. That's the Baxter equation. And then if you make a double loop like that, you can unlace it to this. Yeah, so let's just call it unlacing all. These were understood for the gravity answers. Now they get reinterpreted as a Tuft diagrams of this matrix model with the same functions, so they obey the same kind of integrability relations. From the gravity point of view, you wouldn't really sum over these kind of diagrams because the diagrams are Feynman diagrams. So you don't sum over whether or not two Feynman lines cross 25 times. That's the same Feynman diagram. But they're different Tuft diagrams of the matrix model. So in the matrix model, you need to sum all of these lines. So it's crucial that you don't get new functions of the energy. It is crucial for the answering set. And then there are some other kind of things that can appear, like a single loop on a line. That actually has a divergence. But the divergence is only in an energy-independent part. The other piece of it just looks like the initial function. So everything kind of unlaces to get the same functions of energy we started with. And so the most general model we could imagine that's of this class is one where the endpoint, I only count powers of O, not powers of H. So the thing that involves n O's. So the term, the single trace matrix potential with n O's is, as a function of energy, a linear combination of the endpoint chord diagrams with some arbitrary coefficients. That defines an infinite class of models that depend on these coefficients. But that whole class is integrable in this sense, meaning that if I evaluate arbitrary loop diagrams, the amplitudes I get are the same functions of energy as appeared in the matrix potential. So there's just a kind of combinatorics problem of, say at 4 points, how many 4-point general Tuft graphs, linear Tuft graphs at 4 points unlace to, the crossed versus the uncrossed diagram. So that's a trivial combinatoric problem. We actually didn't solve this one. But maybe it probably has a simple solution, but I'm not sure. So because we didn't solve that problem, we didn't get the specific map from the coefficients in the matrix potential to the coefficients in the amplitude. But at least you know that you're in a particular class of functions of energy, which is just, at any point, at any point diagram, there's a finite list of coefficients. Okay, so it kind of makes this model essentially solve.
Sorry, what's the meaning of the divergence in this class diagram? Like,
Yeah.
is it a divergence at the 6J symbol itself?
Yeah, so there's a divergence because in the loop you have to put you integrate over the energy that sits here, right? These are Tuft lines, and so if we imagine we work at energy eigenbasis, it's like you integrate over the energy of this loop, and the spectral density grows exponentially in the JT case. And it turns out that when you put the 6J symbol decays, but it doesn't decay quickly enough in this particular combination. So it's kind of a diverging but oscillatory integral. One way to try to evaluate this integral is by kind of analytic continuation. So if you said that instead of having the spectral density look like e to the sinh of 2 square root e, but you said it was sinh alpha square root e, then for smaller, I don't know, smaller alpha, smaller than 1 or something. So alpha should be 2, but when it's smaller than 1, the integral will converge. And you can analytically continue around to alpha bigger than 2, and then you find this and it throws out the constant. But that's a little bit like dimensional regularization. You don't quite know what's the regulator. What you really should do, of course, is say that you change something about the spectral density at large energy, and then add some other counter terms, which are only important at large energy, so they compensate, so that the kind of low energy data is not fixed. So that's what one should really do. But basically, any regulator which is compatible with this analytic continuation will give the answer looking like that.
To make this argument, were you implementing the constraint with a Lagrange multiplier?
Well, here I didn't implement. Here I, for a moment, wasn't discussing the constraint. I'm just discussing a more general class of matrix models that don't necessarily have a constraint, but where the matrix potential has a particular form. Basically, looks like it's built out of the 6J symbols. And then the only statement was that that kind of matrix model has this integrability aspect so that the amplitudes are also built out of the same functions of energy. But so far, we didn't get a constraint that will come in a second.
It seems like if you could take that constraint and square it, you might get other things with this without, there would be correction vertices that are not just the 6J symbol.
No, so, well, no, the square of the constraint has kind of a priori 4 terms. One of them looks like delta function squared. One looks like 6J squared, but that relates us to the deltas. So one is like deltas, the other one.
Hello. Can you hear me? Hello, Daniel. Can you hear me?
I hear you.
Okay. I just wanted to remind everybody, this is a colloquium. Okay, go ahead.
Yeah, well, yeah, we're already deep in the weeds now, but yeah.
Emboldened by that, then can I ask if
Yeah.
so I understood that you constrain the matrix model you wanted to reproduce some things first by making sure it agrees with the gravity sign.
Yeah.
But surely there are other consistency conditions on it that you want to get more out of it.
Sure. Yeah, that's kind of coming.
That's kind of,
Well, I mean, in a sense, the thing you more out of it that you might, one of the things more out of it that you get is the higher genus calculation.
so you have this class of each of which would give some answers for maybe there are many completions in gravity side, but is it clear or is the idea that all the matrix models would represent some physical model?
Yeah, good. Well, I think there's a big difference between quantum mechanics cooled to 2D gravity and higher dimensions, which is related to the fact that in quantum mechanics there aren't any constraints of self-consistency, right? Any matrices, any Hermitian matrices acting on a Hilbert space are okay, right? So we can define any ensemble for matrices and call them the Hamiltonian and the operator O and O tilde and whatever, and we can write anything and draw from this ensemble and it's okay, right? So we can't really get constraints. Well, I mean, the gravity side is 2-dimensional, but I mean, a general matrix model may look very strange from the gravity side. Like, for example, it might have a finite spectral range. So there's like an IR cutoff that might say that there are no black holes above some mass. It sounds very weird, right? For example. So most matrix models don't look very nice from the gravity point of do. It's kind of very special matrix models that look nicer, but not nice is a slightly vague term. Right? So it's hard to say precisely what the rules are of quantum gravity in 2D, because they would be dual to quantum mechanics, which doesn't really have any. But in higher D, the situation is very different. This is something I wanted to talk more about at the end, because it's somewhat speculative. But in higher D, we can just, so we could think about the whole goal here is slightly different, right? So let's say we just wanted to ask which effective theories in ADS have unique completions. Effective theory in ADS of fields plus gravity have unique completions. This is like asking which light operator data in a CFT is completable with heavy operators to consistent CFT. And HPPS told us that if we just we study things in perturbation theory, look at the correlators in the vacuum, we don't get any constraints of consistency other than maybe some inequalities on the range of irrelevant operators in the effective theory that are of order what you would expect from like Wilsonian scale. Right? In a way, this story says that you might have wondered, could you get some strong constraints for studying the correlators in a short shield, which corresponds to knowing something about the heavy data. And now the analog, in the sense of HPPS, is really this. But instead of fixing all of the heavy data, it's even weaker. It only fixes the ensemble from which it should draw the heavy data. That's not surprising because it's like e to the s heavy data, so not the all things. But there will never be anything inconsistent in these ensembles. The constraints of consistency, except maybe some inequality similar to what one sees in ADS vacuum, right? But the strong constraints of consistency come if you try to study crossing of the heavy operators among themselves. This is like asking whether the black hole microstate operators commute with space-like separation in ADS. It's not something that you could ever compute from the gravity effective theory. But it is it should be true, I think, for gravity in ADS. It's certainly axiom of the dual CFT, but it should be true in gravity because otherwise there's the arbitrarily long range, infinite range non-locality where somebody does a very complicated operation that acts with the black hole microstate operator far away, and it changes the black hole microstates near you. Which is a very hard thing to measure, but the answer should be zero exactly. And it's not zero exactly, it means that ADS-CFT is wrong. Right? What will go into enforcing those constraints? Well, to compute to look at the commutator of black hole operators, you need to know the 3-point function of 3 heavy operators together. And so you can try to play the same game. You can try to write a tensor model for the 3-point function of heavy operators together with all these matrices. And again, and now actually you can kind of say what the potential is. There's a good conjecture for the potential, which is that just that you take crossing squared for all operators, and that's the entire matrix potential. First of all, it's a good guess because if you take crossing squared and you add it as a coefficient, you can dial to infinity, and you don't get 0 as the answer. It means that the model will obey crossing. So why should there be any other conditions? But once you have tensors, it's much more delicate, basically for the reason why when people tried to generalize the old matrix models to 3D and they wrote tensor models, they weren't able to find a nice continuum limit. So the continuum limit is exactly this double scale limit where you try to take the coefficients in the tensor with model potential to infinity is take the size to infinity. That's where you get smooth, this sort of nice 2D geometries in double scale matrix model case. But in the tensor model case, they didn't get something nice. And indeed, you shouldn't, because well, if you took this, if you take, so what is the tensor model potential? It's actually, it's very easy to write down. It's just the 6J symbol. But so you get a tensor model and some delta function. So you get a kind of matrix plus tensor model where all the potentials are delta functions and 6J symbols. And then you try to dial the coefficient to infinity. And if you succeed, you get an actual CFT. So that presumably means that most of the time you fail. But I have no idea what that really, I think we don't know enough about tensor models yet to say exactly what is that going to tell us about which effective theories of giving completions are. I have no idea. That was going to be the speculation. So I can continue. I know I'm kind of time is running down, so let me try to get sort of to more of the point here. So to get JT gravity out of this matrix model, you need to take a limit in the space of matrix potentials. And that's not surprising because the constraint squared should have had an infinite coefficient. So you really need to dial some things to infinity. And you can kind of see it directly by trying to solve, say, the Schrödinger-Dyson equations, or try to solve backwards for the matrix potential in terms of the answer. And you see that something has to go to infinity. So it's at the boundary of this space of matrix potentials. And a possible, I think, good conjecture is just literally the constraint squared with the big coefficient. But to check that, you have to solve this combinatoric problem that we didn't solve. So it might be that you need higher order terms. And of course, there are many ways that you can approach the same limit to get the same answer. So there are many regulator models that will with the same. So the geometric picture is kind of as expected. You have a 12 diagrams from the 12 diagrams of H build the 2D Riemann surfaces. That's an SSS, and now they're decorated by O lines. And there's all these higher order terms, loop diagrams, but they all unlace so that it just looks like you're drawing, simple O lines on your Riemann surface, potentially with self-cross lines. Now, I think the fact that the model is single trace, when written just in terms of this matrix O, which is the bulk field, and H is really the signature of bulk locality, right? If we had a multi-trace term, there would have been some non-local gluing in the 2D space. So locality of the bulk is what gives something single trace. And in general, obviously, if I have a single trace multi-matrix model, integrate out some matrices, it looks multi-trace for the rest. So if we had been in higher D, where we wrote a matrix for every operator, including the multi-twist operators, then it would be special property of the holographic ones that when you integrate out the multi-twist operators, you end up with something that still looks single trace for just the ones whose fields you see. Now, because of the divergences in this one, again, there are two places of divergence. One of them was in those loop integrals. Just at this level, there are two places of divergence in those loops, which came from the large energy integrals, and in the fact that the potential had to be scaled to infinity to actually reproduce JT plus matter because it had a constraint, so it's at the boundary of the space of consistent ensembles. The second thing was easy to understand, right? It's basically just adding something with a big coefficient as the matrix potential. How would you try to regularize the integral over energies? Well, there are many ways of doing that. One thing which is interesting to study in its own right is this so-called Q-deformed JT gravity, which is really a set of rules for computing the disk amplitudes, where you replace the 6J symbol by the Q-deformed 6J symbol. And it came up in the double scaled SYK model. So we take the SYK model with product of P fermions and scale P a square root of n, where n is the number of Majoranas. And then you make the operator out of a product of A, where A also scales with A. And then the correlation functions of that particular O look like they come from the same chord diagrams, but with Q-deformed 6J symbol, which is some complicated special function.
Don't they also have different spectral density?
Yeah, it also has a different spectral density, and in particular, it's cut off at -1/log Q, which is a number, which is Q is between 0 and 1, so that's some specific finite one.
What's the physical meaning of this Q deformation in the bulk that changes the spectral?
I think that's really an open question for the most part at this point. But some of what I'll say today might give some answer.
But how do we know that banks skewing this random matrix?
Well, I'm going to describe it with the matrix ensemble that matches those guys.
But the higher genus computation.
Oh, right. So I think this Q-deformed JT gravity was not defined in higher genus. So we can make up the rules. The matrix model will give a particular answer. What this answer looks like is that you draw chord diagrams on the higher genus Riemann surface, and every crossing comes with the Q-deformed 6J symbol, and the particular way of integrating the B's, which is basically the B integral is replaced with discrete sum. Because the range of energy is finite, so B is kind of a Fourier transform of the square root of the energy. So the range is finite, B is discrete. So that's the answer. But what bulk theory produces the local description or string theory description. So in a way, this is a case where the matrix model can give you the definition. It's the best definition. Because the energy range is finite, it's a standard Toff scaling in the matrix model. It's not a double scale model. Now there are no divergences at all. So there's no constraint. In other words, when you try to replace the operators, if you do it twice, the crossing thing. So you see, in the JT case, if I take two operators and I switch them, it comes with a 6J symbol. Then I do it twice, it comes back to itself. So the physical states are like the symmetrized states. They're like invariant under the switching. And there's a kernel. And the kernel being 0 is the constraint. But the Q-deformed 6J symbol doesn't obey an unlacing. So I do it twice, I don't get back to itself. It's smaller, kind of. And so the different orders are just different. There's no constraint on the matrices, it's just some model. And that makes it harder to solve because every diagrams don't unlace to the same functions of energy that you started with. But you can construct the matrix potential order by order, for instance, at small q, which is the opposite regime. And in various ways, we convinced ourselves that the matrix ensemble exists for any q between 0 and 1, and other choices of parameters. I don't want to go into too many details on that, especially given that the time is pretty much up. But I just want to explain this. Is your question? Right. So what does the higher genus story look like? So of course, on the gravity side, you would want to integrate over the moduli space of your constant curvature Riemann surfaces, include the scalar loop determinant, and the scalar determinant can be written using the Selberg trace formula as a sum over geodesics, which include ones with self-crossings in general. And then for every geodesic, we can kind of blend it n times, and there's this specific formula. And then there could also be amplitudes with external insertions, and then again, you will sum over all geodesics connecting them, with again the rule that every crossing has the 6J sum. So that's the gravity computation. And if we have primitive geodesics, the ones that only wrap once, then the matrix model kind of works in a very simple way. Let's say I have the circle in the double trumpet. That's just the propagator of the matrix model. It gives me this factor. This reproduces this simple Selberg formula here, which is just the length of this line. Or in something more complicated, like this figure 8 in a pair of pants. Now it's a function of 3 energies. You get the 6J symbol. And it turns out you can write this XJ symbol in sort of B basis. B is the length of this GNSX. And it turns out to be just a simple number, which is exactly the length of this geometric geometry. So that's kind of an example of how it works. But the complicated part is the multi-wrapped ones. And the way the multi-wrapped ones go actually depends very sensitively on how you take the limit in the space of matrix dimensions. And the reason is, and this is a little bit of a heuristic sketch, like, so basically to fully understand this story is like asking to do matrix model recursion for multi-matrix models. And we kind of derive that, but piece by piece by, in other words, what you do is you say you have a given topology of the Topf diagram. You will have all of the H Topf lines, which you imagine that are taken care of. And then you want to sum where you put the O lines. And you classify the diagrams by how many O lines cross in certain places. First you study the one with like one crossing, then the ones with two. It's kind of an iterative procedure. In this way, you can build up what the whole amplitudes look like. But it's very complicated to make sure that you don't overcount the same diagram, because maybe you have one which crosses with two lines, but somewhere else is one. So it's very complicated. But to slightly oversimplify, let's say we had a double trumpet. This is a double trumpet on the side. I'm going to glue it around this way in this trace. That will make it a double trumpet. Here I decorated it with a crossing. So I have O sorted on one side and O on the other side. So this is trace O e to the minus beta h squared. I want to connect the contribution, and then the green lines are the other O lines of summing. And here's like one kind of structure. For instance, it could look like this. But in general, I can get this by gluing together disk amplitudes, because I kind of cut here. So this looks like a O disk amplitude with 1, 2, 3, 4, 5, 6 O insertions, except that if I should take the amputated disk amplitude, where I remove the 2 to 2 propagators, and then to compute this, I should include them with one factor of the 2 to 2 propagator. Just like how I compute loops always, I should take the truncated truncated vertex, and then solve them with propagators. So if I have a loop, I get only one propagator, not two. So when I do that here, I have to compare it to the full disk amplitude. I need one factor of the inverse propagator when I glue. But the problem is that the propagator, the 2 to 2 propagator, has a kernel because there was this constraint for the true JT coupled to MAC, the unregulated field, what I want in the limit, right? Because it was a symmetrizer that said that only the symmetrized two particle states propagate. There is no anti-symmetrized two particle state because it's a bosonic field. So this guy, the truncated amplitude, has an infinity. If I look at the space with, the truncated amplitude is 0 between anti-symmetrized states, but the inverse of the 2 to 2 propagator is infinite between them. And so how do you evaluate this expression? And so it really depends sensitively on how you approach the limit. So that's a little bit of a solid. Here, and we get different answers depending on what we do. So if in a regulated model, there's a way of regulating, a way of approaching the limit, maybe a better way of saying it, which leads to the result that the zero of the anti-symmetrized part of the amplitudes is stronger than the zero of the propagators. So then I only get the symmetrized states contributing in this double trumpet calculation. That's the Selberg-Janssen, right? The Selberg-Janssen is computing the determinant of the matter theory. It looks like counting the number of states on global ADS2, which is wrapped into look like a cylinder, and the field is a bosonic field, so the operator like this and some other order is the same operator. That's the constraint, basically. So one can get that answer. But actually, if you had studied this Q-deformed theory, and you take the Q goes to one limit, you don't get that answer. So the Q-deformed theory only gives you the disk, at disk level, it approaches in the limit JT gravity, but nobody said that at the loop and the double trumpet it did. And the point is that when you do this double trumpet computation, you're counting all of the states. Whereas if you're computing the disk amplitude, you're only, if there are states that decouple, you count them in the double trumpet, but they don't affect your correlator in the disk. Okay. So in that sense, there's, this cannot fully determine the double trumpet. In this case, actually, the result is that you don't get the symmetrizer at all. The symmetrizers kind of cancel. And so the Q goes to one limit of this Q-deformed guy tells you to count every order of the descendants of O as a separate state. So it has an exponential growth in the number of states being counted. You get a geometric series from the primitive winding. So it's like a distinguishable particle statistics. It corresponds to a Hagadorn growth of states, like in string theory. And so there is if you evaluate it as a function of B, there's a finite B with the answer diverges. Of course, when Q is less than 1, the B integral itself becomes like a discrete sum. And there's some interesting behavior depending on if Q is small enough, then everything is finite. As you start to increase Q before you reach 1, you find that the original saddle becomes unstable. And maybe it's like you want to have a winding compensate, right? That's sort of what's suggested because we have this aggregate. So probably this seems to be the matrix model telling you that this Q-deformed JT gravity is really some kind of straight thing. But there's still a lot to be understood there. So I'm kind of out of time, so let me try to just wrap up what was the point. So you can think of, if we take JT plus scalar as an effective field theory, then we can reproduce everything from some matrix model. It would be nice to understand in more detail what kind, exactly how to map regulators of the UV in the bulk to, deformations of the matrix model that eliminate these divergences in the loops, which look like the short distance divergence and the divergences in the intervals of the UV. So what exactly is that mapping? It would be nice if we could fully solve that class of integrable matrix models, then I could definitively tell you what was the matrix potential, instead of just enriching that. I think it would be amazing to understand the story in higher D, where I think is a very similar structure, where we can write a matrix model for the dual of gravity in AS4 with a massive scalar or something. Arbitrary effective Lagrangian in the bulk, and then you'll be able to write a matrix model graded by spin whose correlators at, first of all, this level reproduce the Schwarzschild correlators, and then the higher genus ones look like certain kinds of higher, someone with certain kinds of topologies. It would also be great to understand the story where you include 3-point functions of 3 heavy operators, as I mentioned. Answer the previous question, and that's also presumably where you might see constraints on the gravity effective theory. So I think that's really an exciting direction, as well as understanding more what this thing is telling us about this Q-deformed. So that's all I have to say. Thanks.
I have a question about this ruling the double trumpet as like ruling with translation.
Mhm.
Even without operators, even without methods, that have some issue of the method classical.
Yeah.
So
Um,
deal with that.
well, right. I mean, that's true in the like geometric computation. But here I'm really talking about the matrix model computation. So I'm just trying to do the matrix model computation like cool. So somehow it takes care of this automatically. Yeah, I'm not exactly sure. Yeah, what's the right way to say it? But
What's the meaning of this doing without matter? Maybe is the question at the level of the matrix integral of the diagram we showed before. So there you were cutting the trumpet with a geodesic like this, right? With a single geodesic to get a disk like object.
yeah, so okay, so let's suppose I wanted to do the computation of something without the O insertions, right? That's where you see the problem. And then where does that come from in the matrix model? So in order to get an unambiguous result from the matrix model, we have to know what was the measure for the matrix. And in particular, you know, they say in the usual way of discussing the ETH, they write this random matrix R, which is related to O by some scaling by function of energy. If you said R was the matrix, that's a different measure than if we said O was the random matrix, and they differ by function of two energies, which changes the double trumpet with no insertions. So in that sense, it's part of the input data. If we would take the model where the matrix O has the flat measure, then you can compute the, you know, the double trace kind of correction. It just comes from the quadratic part, and it gives you, you know, this, you know, just the propagator factor, which is, you know, the gamma log of the gamma function, and that's the correct answer for the single. That corresponds to doing the, I mean, that will correspond to the Selberg formula, where instead of having the correct Selberg sum over geodesics, we sum every operator that runs around as if it was independent rather than opposing symmetrization. So it's like the Selberg guy if you had a Haggerty spectrum. That's what you get. That matches with what you get with insertions in the Q-deformed case in the limit. If we really wanted just JT coupled to matter, then we have to say that the measure was something else. That we had the flat measure not for O, but for the thing that gives you the correct double trumpet with no insertion. So in that sense, it's a separate identity from the disk. But I'm pretty sure that if you had started with the model where you wrote a matrix for every operator, not just for O, but also for O, del O, and so on, then when you integrated them all out, the measure you would get is the one that would look like the usual, then you would get the Selberg answer even with no insertions.
Is there a matrix integral interpretation for the problem where you don't include the one with determinants?
I see it doesn't do any good to raise my hand.
Well, shall I answer Douglas's question?
Let me ask a question.
Okay.
No, I've been raising my hand for a while. I frankly did not understand very much of this seminar. It wasn't a colloquium, it was a seminar. But that is at least in part because because of the format of the Zoom. But let me ask my question anyway. You said, I think, that if you take a Gaussian model, a quadratic model, that it becomes some sort of system which scrambles in 0 time?
Yes.
Okay. You also said that if you add something, which I think was a quartic construction, that it could be made into a conventional fast scrambler.
Yes, that's right.
Okay. Is there a situation that you can construct where it will be made into a scrambler which scrambles in the thermalization time?
Faster than a fast scrambler, in other words. Yeah.
Thermal time, inverse T, inverse temperature.
That's an interesting question.
Well, I know it's, yeah, it is.
I'm not entirely sure. I don't see.
The level scale as well can be complicated, so you can see our data.
Yeah.
Say it again.
Point. Yeah. Yeah.
What was the comment? Repeat the comment.
Oh, that the double scaled SYK model has that property.
We believe it does, yes.
Since the double scaled SYK can be obtained from a different matrix model of this type, then that physics can be obtained.
Okay.
Yeah, I agree with that.
Okay, I think it's an interesting question. Whether there's a matrix model of the kind you're talking about, which generates what I call it hyperfast scrambling, but it's scrambling on the thermal time.
Yeah, I mean, somehow from the matrix model side, there aren't, I mean, at first glance, it looks almost like you could get any light correlators, any low point light correlators you ask for, you can try to get from some matrix ensemble. But I mean, that's
right.
So, but I mean, there of course there might be some kind of constraints. It might also depend on whether you demand some kind of stability of the samples of the matrix model, then you'll get more constraints and so on.
Okay, so I might ask you a little bit differently. If you construct a thing which has scrambling in the thermal time, is there anything else which is interesting about it that jumps out and says this model has some interesting structure that we should pay attention to?
Yeah, I mean, so I guess I would say so. Let's look at the model which scrambles instantaneously.
Yeah.
The model that scrambles instantaneously is really like the one where there's no constraints relating to matrix for O and H, and then every operator order of O is a different operator.
Yeah.
You know, kind of like in quantum mechanics, the operator order matters. You can't drag one around the other. And so you always get some Hagedorn-like spectrum of operators, and then when you do things like the double trumpet, which count the bulk states, look like the trace over the bulk states roughly, then you find a pole at finite temperature because Hagedorn. I think that's probably typical of situations which are ultra-fast scrambles. So my guess is that I would see something.
Okay, we're distinguishing now fast, hyperfast, and ultra-fast?
No, I was distinguishing between fast and and hyper-fast, but not another distinction.
Okay, but you were talking about something which was much faster than the thermalization scale.
Well, right, but I mean, yeah, that's true, but I'm not sure. Okay, yeah, so once, yeah, then I'm not sure, but I mean, but again, like as Jafferis said, since the Q-deformed, since double-scaled SYK looks like that, and that looks like that is this Q-deformed JT, it has this kind of matrix model, that guy has a Hagedorn-like spectrum. The answer is probably that's the hallmark. It's a little puzzling, of course, because usually we think that we might say that stringy corrections are what makes the scrambling slower, but Yeah, these models also have some stringy spectrum. But
Oh, I think they have a huge amount of stringy spectrum. Yes, I think that's exactly right.
yeah, so,
Hagedorn-like, yeah.
yeah, that's right.
Thank you, Daniel.
Well, I forgot what Douglas's question was, and he's not
Yeah,
here.
they are matrix model without including the block groups.
Oh, right,
Like both methods.
right.
But
Well,
just not include.
that is somewhat hard to achieve. Well,
Just, so that you don't have the divergence. Manually.
Sorry to ask a question about the question, but.
I think, yeah, behalf of Douglas.
well, also Douglas isn't here, so maybe should I wait a minute or does he have to go?
Usually, if you describe the possible, your estimate, you know.
It wouldn't be a local bulk effective theory. One step over, you can just exclude those diagrams.
Sure, yeah, so that would
See
be.
what?
Yeah,
But there are two ways you can do it. Like when one is just looking at the theory, just have it without just requiring a small group. And okay, then there's a separate question I want to make a comment. Maybe is Kita has this idea that to make this gravity UV complete, you can add a ghost field. So that cancels the UV divergence.
yeah,
He was mainly talking about the SYQ, which is UV complete. You have a bulk fermion, but then a ghost fermion is another combination, so the cancels.
yeah,
And so that I think will be very natural.
yeah,
Well,
sure.
together, it probably
It's-
equal to some other.
Right, I mean, maybe the ghost here is actually, I mean, it corresponds to a Grassmann matrix in this matrix model, in the sense that you want something whose matrix determinant cancels. Right? So you take some very heavy guy like that, very heavy
Well,
anti-commuting matrix.
yeah, like the same mass.
Well, it doesn't even have to be, it doesn't have to be the same mass. It could be much heavier because at small b, the mass doesn't matter very much. But probably, yeah. Yeah, so
If
yeah,
the
you could,
mass is similar,
you could do
effectively
something
can
like
share
that.
without the bulk groups. Effectively, I can share without the bulk groups.
Well, I mean, that's the same. So if you take the two things that have the same mass, so that it cancels all the bulk groups.
But with
Then-
different boundary conditions, so that's you have some boundary.
But you need that higher genus thing, so you get.
But it's a lot.
No, but what I was going to say is, let's say you take exactly the same story, but with another matrix that you say is Grassmann. So then you just, in terms of closed diagrams, like bubble diagrams, it just cancels. But but imagine I integrate out the other matrix. Well, then it induces something which looks like a double trace interaction for H, but maybe also more multi-traces in general, depending on the details, because the other matrix will also have to involve self-crossing if you wanted it to cancel exactly at everything. So from that point of view, it's now some like complicated multi-trace model. Like it involves multi-trace things for H, which are designed to cancel every time there would have been an O loop. In that sense, it sounds local, unless you include the other operator. But maybe something that might be a bit nicer is to add another operator which is very heavy. that will probably have the effect of removing the divergences at small d, because like the UV central charge could be 0, but it won't kill all the loops of low energies. That's more, that's kind of what I have in mind. That's an example of how one would try to treat the thing as in the sense of an effective field curve. So you add like some other guy that will cancel everything at very small b, and then you could either keep it or have to grid now.
Yeah, there's no divergence because it's D is discrete, right?
Yeah, there's no divergence, and also, well,
Is that automatic ensemble
I should say in the Q-deformed case, it's a little more subtle. So if you write the matrix model for the Q-deformed JT, well, so Q-deformed JT is not exactly the same as double scale SYK, because double scale SYK has every operator applied to the A for all A, whereas Q-deformed JT has just one. So they're not exactly the same. In the matrix model for Q-deformed JT, for Q like small, like close to 0, less than some critical value, then everything is finite in the genus expansion of the matrix model. But if you increase Q past some critical value, you find that the saddle becomes unstable. So it's like at the top of the potential. And when you pass to that point, then the double trumpet has a divergence. But it's only at this particular value of Q. If you go past
Is the critical Q correspond to a half? Q squared equals a half of n? Q squared equals a half of n?
It's a different.
No, it's a different. It's oh yeah. It's not
P squared
that
equals a P squared over n equals a half.
Actually, I'm not sure. Yeah.
Okay.
Yeah, I'm not sure. What do you expect happens at that value of Q?
Well, I'm not really sure, but I think maybe that the scrambling goes from what I call hyperfast to what I would now what I would call hyperfast to what I thought you were calling ultrafast.
Okay, I see. Oh, that's interesting. Yeah. That's conceivable. I'm not sure. Yeah. But anyway, in some range of Q, the saddle is stable. That's the small enough Q. Then for Q bigger, then it looks like the saddle is unstable.
Mm-hmm.
Maybe you don't care. You say you pick some contour matrix model, and you take the saddle. If you do computations there, you get some finite answers.
Good. Thanks.
Yeah, sure.
I think we've had a lot of questions. I'm sure there's time for discussion over the next day and a half or so, but let's thank you again for